Chapter 7 Friction Part A. This is our last chapter in our course, so please pay attention of this chapter. In this chapter, we will divide it into two parts. The first one is Part A, which covered laws of dry friction, coefficients of friction. And the second part, which is Part B, we will cover wedges, screw friction, and finally we covered rotation friction. So let's move to the part A, the laws of dry friction, coefficients of friction. So in this part, we will cover the laws of dry friction, coefficient of frictions, and then we have angle of friction, and then we have dry friction, and finally we have a sample problem. So the application of friction basically is very useful in many engineering applications, such as tires, brakes, and also for the application in ski and the sports or motorsports. So in the introduction, the friction is the force resisting the relative motion of solid surface, fluid layers, and materials elements sliding and sometimes rolling against each other. There are two types of frictions. Basically, we will cover a dry or column frictions, and we have a fluid friction. Fluid friction basically apply to a lubricated mechanism. So in this chapter, we only covered a dry or column friction. So we don't cover fluid friction. The present discussion is limited to dry friction, basically, okay, between non-lubricated surface. So we can summarize by using this diagram. So we have dry friction. So basically, dry friction will cover the first is static friction. So in equilibrium condition. So and then we have a dynamic friction, which is sliding and rolling. So in this chapter, we will cover only static friction. So for the next course or next subject, which is dynamic, maybe you will cover for the moving object related to sliding and rolling. So the laws of dry friction for the coefficient of friction, basically we will cover from the equilibrium of object. So basically when we talk about the block of weight, W is placed on the horizontal surface, okay, as you can see in this diagram. So force acting on the block is weight, basically is weight, W downward due to the gravitational force, and reaction of the surface, which is we call it N. So this is obey to the Newton's third law, which is action and reaction is equivalent, which is the same magnitude, but the opposite direction. Small horizontal force P is applied, okay, as you can see from this diagram. For the block to remain stationary, in this case, we can see that there are several conditions takes place. If the P is less than the friction, the object will stay in place or not move. If P is basically equivalent to static friction, is about to move, and is also we have the P is greater than static friction, the object will start we will start to move. So in this case, for the block to remain stationary in equilibrium, the horizontal component F of the surface reaction is required. So when we apply P, there is a reaction from the surface that we can show as F, where F is a static friction force. Okay, so the static friction force, there is a certain range number, so there is up to the maximum friction force. Okay, so if the static friction force at, exit at the limit of maximum level or maximum limit, we call it Fm. So basically, if there is a calculation for the static friction, we will just put Fs, and at certain condition later on we will see the using of Fm. As P increases, the static friction force F increases as well until it reaches a maximum value of Fm. So mu s is a coefficient of static friction. In order to determine the value of Fm, so it's required us to have the coefficient of static friction multiplied by n. So that n is a normal force produced by the y-axis in this figure. So during the process of determining the Fm, so we need to identify the value of n. So it depends on the condition of block. So if the block is in the horizontal position, so we need to take into account of the y-axis. Okay, in this case, we have the n value is equivalent to W. So if we apply another force, let's say downward force, let's say, so we will give the additional uh, uh, force. So we need to taking care of this force. So the n is no more equivalent to W, so it equivalent to W plus P, okay, additional force. So later on we will see what will happening to the block if we put various condition or various P external force at a certain angle. So further increase of P causes the block to begin to move. As F drops to the smaller kinetic friction force Fk, so when we start to move, the static friction actually become as a kinetic friction. As mu k is we call it coefficient of kinetic friction. As you can see, the formula is the same but different in terms of the coefficient, whether the static or kinetic. So the maximum static friction we will state as Fm equal to mu s n. For the kinetic friction, we will state as Fk equivalent to mu kn. So as you can see, if you compare to the static friction coefficient of static friction and between coefficient of kinetic friction, the value of coefficient of static friction is higher than coefficient of kinetic friction. So the maximum static friction force and kinetic force are basically depend on the, if we draw a graph, so it's the proportional to normal force, and it's depend on type of condition of contact surface. So the type, that's mean the whether the contact surface between blocks and rubber block and wood is depend on, so it will produce the coefficient, different coefficient between them. And also independent of contact area. So how big the surface area is, no, doesn't matter. So the point is the static and kinetic friction is depend on the coefficient and normal force. So the normal force actually is depend on the external force given and also the weight. So if the mass is bigger, it will produce the bigger static or kinetic friction, and also for the coefficient of static or kinetic friction. If we see from the various value of coefficient of static friction or dry surface, so we can see from the contact of metal on metal, metal on wood, metal on stone, metal on leather, or different contact with wood on wood. So we can see there is a various value of static friction, coefficient of static friction. So if we observe the value of coefficient of static friction, the higher is produced from the contact from rubber on concrete, okay, around 0.6 to 0.9. So the lowest, the least value actually from the contact metal on metal, okay. So if you compare um, maybe if we have a contact between the surface of ice or something, maybe we can assume that there is a frictionless. So there are four situations that occurs when a rigid body is in contact with the horizontal surface. So we will cover four situations. The first one is no friction applied, no friction produced. If we still apply for external force, let's say we have a external force P downward. Okay, in this case, although we apply a external force P downward, for the static friction is doesn't exist because of only apply at y direction only. So the movement is not taking place here because of the movement is on x direction, x axis only. So the value of even the how many external force we give, so there is a no friction applied here. So in this case, for the y value, okay, to determining the n, so the n is equal to p plus w. So we have this in equivalent. We have three direction or three forces acted at the equivalent. So the n is positive direction and p and w is a negative, which is downward direction. So as a result, we have n equal to p plus w. Or in case of the external force applied at a certain angle, so in this case, we can see this applied this downward direction, whereby it will produce the component of px and py. And also there are many external force can be applied, whether from this direction, okay, or this direction or this direction. Is basically we will understand on the component or in equilibrium, okay, forces acted on this system, so we can easily solve this problem. Okay, in this case we need to apply a free body diagram first in order to look at the x and y axis. Okay, for in this condition whereby the value of x-axis is produced by the component of px. Okay, so we have px to the left, to the right, and we have f to the left. So the value of f is equivalent to px. Okay, and in this case, the value of px is very uh, small from the uh, static friction, so it will make the box is static. So in this case, once we get the value of n, so in order to get n, we need to calculate the value of w plus py here. So once you use the theorem Pythagoras to get the value of py, and then you add w and you obtain n. So in order to calculate the static friction, okay, this n must multiply by mu s, and this static friction is basically, if in no motion, this value is higher than f value or higher than px value. So the next condition is a motion impending. So we can see that the block is about to move. Here we draw a free body diagram. So we look at the x-axis and y-axis. In case of y-axis, we determine the value of n, which is the same as the previous diagram, which is py plus w. And then we compute the value of static friction, that the n multiplied by mu s, and we have in this condition, the static friction is at the maximum value, so that the value of Fm is equivalent to value of Px here. So once the value Px is greater or bigger than Fm, the block will start to move. In this case, we have the Px is greater than value of Fm, so the block will start to move. Once it start to move, the static friction turn to be a kinetic friction. So this is the diagram, shows the condition of various condition of when the value of P start to increase. And if we can see from this point of no friction, so basically the value condition is start at here. So once the value of px is start to increase, it will basically is a linear process. Okay, and it will reach at this certain condition, whereby at this point we have the value of fm is equal to px, and one is start to move, the value of fm is start to reduce. Okay, so and then we will see the value is start to be constant. So when we want to uh, differentiate or to look at the difference between the friction, kinetic friction, and static friction, so the value of static friction is higher than the value of kinetic friction. In this case of the value of the value of from the coefficient of static friction is higher than coefficient of kinetic friction. So sometime we will try to relate between the normal force and friction force by using a resultant R. So in this case, we will see to the motion impending. So in this case, we can see the Fm divide by n value is equivalent to W plus Py. So and then this value is basically the obey the rules of Pythagoras. Okay, so we can look at the connection between Fn and n. So it will produce the tangent theta. So the tangent theta basically is equivalent to Fn divided by n. So also the value of mu s. Okay, in this case also the same thing. So sometime during the process of solving problems, we need to use this kind of relationship between the normal force and friction force in terms of tangent theta and mu s or mu k. So let's consider the block weight W resting on board with a variable inclination angle. So previously we looked at the horizontal whereby we have a theta is equivalent to 0 degree. So in this case, what will happen to the block if we put at a certain angle, okay, theta. So the first thing we will cover of the different type of condition. The first one is no motion, and the second one is about to move or motion impending, and the third one is a motion. So uh, for the easiest way to highlight about this, let's see we have a block or a box we just put on the inclination plane, and let's see what will happen to the block. There are three conditions. The first one is a no motion, and the second one is a motion. Okay, so the first thing we need to solve this problem is to look at the free body diagram. Okay, in this case of the inclination angle, so we assume that the x-axis is basically in this line, and for the y-axis is in this line. Okay, the perpendicular 90 degree of the surface. So in this case, for the uh, y-axis, basically we will have the value of n. So the n is a perpendicular line to the surface. So for this, in case of theta equal to 0, the n basically here for this case, theta with the certain angle, this direction, okay, or this direction. Okay, and then for the weight, basically, no matter how the object incline, the weight is supposed to be at the acceleration of gravity. So this direction, okay, this direction. So in this case, the weight we can dissolve for the its component. So we have the value of weight of y, w cos theta, and then for the x is w sin theta. Okay, and for the this w cos theta and w sin theta will give the effect for the whether the object move or not. Okay, the first thing we need to do is to get the value of n, and then we get the value of friction force, and then we try to look at the value of the x direction, whether this value w sin theta is bigger than frictional force, it will start to move. if this value is smaller, it will not move. Okay, so it depends on this free body diagram. So in this case of y-axis, we have the y cos theta here, and then the n is equivalent to this value. So the n is supposed to be w cos theta. Okay, after this we will see the how to tackle the problem related to this. Okay, in this case of the motion impending, or is also the same thing. So the value of w sin theta is basically the same as the frictional force. Okay, and in this case of motion, w sin theta is basically higher than the frictional force, or bigger than the frictional force. So it will start to move. So problem involving dry friction, basically we are given all forces, okay, all forces given. So including the coefficient of static friction. So the question is asking for the determine whether body will remain at rest or slide. Okay, and also different question, all applied forces are given. So motion is impending. So determine value of coefficient of static friction. So there is a opposite from this. Okay, this one coefficient of static friction given. Okay, the uh, determine the body at rest or slide. Okay, in this case is the opposite. So another question be from this. So the coefficient of static friction is given, motion is impending. So need to determine magnitude or direction of one of the applied force. So in this case, applied force given. So what is the value of applied force? So here we will go from the very easy problem, okay, sample problem, to the quite difficult, and we try to cover very various type of question. So in this case, problem number one, 6 kilogram box it at rest on a table. So the static friction coefficient mu s between the box and table is 0.4. Then 20 newtons horizontal force is applied to the box. Okay, the first one is draw the free body diagram on the box. B, determine normal force. C, determine whether the box move or not. First thing we need to draw a free body diagram. So we just draw something like this. So need to indicate the weight, the normal force, and also the frictional force. And for the normal force identification, so you need to identify the value of n first. So in this case, the value of n is actually the same as value of w. So very easy, you calculate the w equal to mg, and you get the value of n equal to 68.86 Newton. So for the determine the box is move or not, so we need to get the value of frictional force. Okay, once the value of frictional force, we put the uh, equation and we substitute the value, and finally we obtain the value of frictional force 23.54 Newton. So in order to look at the whether the box it move or not, so the frictional force is the value of this. So the applied force, external force given 20. So the value of static friction is higher than or bigger than 20 Newton, so that the force given is not enough to move the box. So as a conclusion, the box is not moved or static. So let's go for the problem number two. So the same thing, the same condition, the mu s is also the same, but given the a different value of force at a certain angle, 45 degree. So what will happen is try to make a free body diagram. So we have the force 60 Newton at the 45 degree. So we need to dissolve the to its component x and y component. So for the fx is f cos theta, fy is f sin theta. So in order to get the normal force, so here is no more normal force is equal to W. So because of the existence of external force given at the 45 degree, so we need to take the value of Fy also. So the normal force is equivalent to W plus Fy. So W is equivalent to mg, Fy is equivalent to F sin theta. So we substitute the value, we have the N is equal to 101.29 Newton. So for the determine whether box move or not, so we need to calculate the frictional force, static frictional force, and also to get the value of fx. Okay, fx we obtain 42.43. So basically the value of 42.43 is higher than the value of static friction once we substitute to the equation. So we can conclude that the fx is bigger than fs, so the box will move. So one is moved, it will produce a coefficient of kinetic. Okay, so you need to calculate the value of kinetic friction. Okay. So problem number 3, this problem related to the inclined plane. So that we have the flat screen TV box with a mass of 100 kilo, and we have the RAM is 23 degree. So the first thing we need to draw a free body diagram, and then next we need to get the box move up to the RAM if the coefficient of static friction is 0.2. Okay, what is the value of P? We need to put or to give in order the box start to move, okay, to move up. So basically produce a free body diagram. Okay, in this case we have the weight. So the weight is basically have is a component x and y. So for the component x, basically we have w sin theta, or this value can be put here, okay, because the value will start to slide down. Okay, and then we have wy, so w cos theta. So we have the x axis, we have only the value of wx, fs, and p. Okay, so that we need to determine to get this condition, and also for the y axis we have n and also wy. Okay, so for the force needed to get the box moving up, so the first thing we need to get the value of n. So in this case the value of n is equivalent to wy, which is w cos theta, and we substitute the value, we get n is equal to 903.02 Newton. For the x axis we have the wx, basically equivalent to w sin theta, or mg sin theta, which is 383.31 Newton. This is one is for wx. And once we get the value of a normal force, we can easily to get the value of static friction. So we substitute the value and we multiply by using coefficient of static friction is 0.2, and we get the value of friction force is 180.6. So basically the P value we need to give is basically the combination of the static friction and Wx. Okay, so we have the arrow here. Okay, arrow, two arrow value, so we need to plus to add these two, 383 and 180, so we will get the value of 563.91. This is the value of P need to produce or higher value. So the P is supposed to be the higher from the value of 563.91. Okay. So the problem 4, we have a different also in inclined plane, but in this case we give the value of P horizontal compared to this line. Okay, so it will produce the angle. Okay, if we refer to this plane. So the first thing we given is 50 kilogram of block, and the static friction and kinetic friction is 0.3 and 0.25 respectively, and find the magnitude and direction of the friction. Okay, the first A is given P equal to 150, and B given P is equal to 400 Newton. So in this case, for the free body diagram, so we will make something like this. So for the P is equal 150, we have the uh, uh, triangle produced. We have PX and PY. The PX is the same as this line, and the PY is in the Y axis. So as you can see that there are three red color arrow. Okay, and indicates the X axis force, and blue color arrow indicates the Y axis forces acting on this. So in order to get whether the box will slide down or move up, so we need to get to look at the equilibrium condition. Okay, so for the equilibrium condition, we can start to look at the fx equal to 0, and then we will look at the fy equal to 0. In this case, for fx equal to 0, we have a three red color arrow, so that means we have wx, okay, and px and f. So f, we don't have the real, we don't not sure whether the arrow is sliding down or sliding up, so we just assume that it's sliding down, and these two value is we sure that the value. So from this condition, we have wx plus f, okay, and then minus px, and then we start to substitute the value, and finally we obtain the value of f is negative 26.881. So basically the f value is this sliding up, okay, to the value, so that we have the f value. The f value basically this is not the frictional force. Okay, the frictional force can be Fm. So the maximum value of frictional force may be this is the frictional force is whether the value is maximum or minimum. So we don't know. Once we get the value of n, so we can compute the value of static friction by multiplying the value of coefficient. So in this case, by using the Fy, we can easily get the value of n. So for the Fy in red, in blue arrow here, we have one upwards n, and then downward Wy, and also Py downward. So assume that this value is positive, this value is negative. So we have n minus Py and minus Wy. So we substitute the value, and finally we obtain the value of n equal to 512.22 Newton. So and then we start to calculate the value of. So the static friction, actually the value of static friction is the maximum value, whereby the value is 153.67. So this value actually is higher than the value of we calculate just now at fx is equal to 0. The value is here. So the fm is higher than is bigger than the value of f. So we can conclude that the block is equivalent. Okay, it's not moved. In this case of P equal to 400 Newton, so the free body diagram also the same thing. So the Fx is equal to 0 is the same thing, but we need to substitute the value of this 400. So and then finally we have the F value is 208.12. Okay, in this case for the N is basically also change. The equation is also the same, but change to the 400, and finally we have N equal to 597.73 Newton. And then we the value of Fm. When we substitute the value, we get the 179.32, and in this case is basically the value of F we managed to get from the net force of Fx equal to 0 is basically is higher than Fm value. So we will conclude that the block will move up. Okay, and since the value of Fm is or F is bigger than Fm, so actually the block start to move. It will change to the kinetic friction. So once we get the value, the box start to move, we will change to the value of coefficient of kinetic friction 0.25, and then we multiply by the value of n. So basically we have the value of kinetic friction is 149.36. So this is for the different applied force at a certain condition degree. So maybe you can start to calculate from this exercise one. Okay, given the force acting on the inclined plane of the box weight of 300 Newton. Okay, try to get the answer. So another question in problem 5. So we have the condition of the in equilibrium condition of a box connected with the pulley and wired or cord. So in this case we have ABC box or mass. Mass A is 15 kilogram and mass B is 6 kilogram, and then given mass C on top of the box A. Okay, and then given the coefficient of friction between between A and table is 0.3, and assume that there is no friction between cord and pulley. So determine the minimum mass of C in kilogram that must be placed on A to prevent its move from moving. So we will assume that the moving is from the to the right. Okay, A and C will move to the right due to the weight from the vertical mass from B. So in this case, basically, we try to divide into two parts. The first part is a equilibrium from the horizontal, whereby we have the uh, tension T1 and then friction Fs from this system of mass A and C. And the second one is the from the system of vertical from the mass B. We have Ng and we have T2. Okay, the tension force from the T2. So in this case, we have two equation. So from produced from the Mg Mbg equivalent to T2. This is one equation, and also the another one is T1 is equivalent to Fs. And we know that T1 and T2 is the same value. So that in order to get uh, the value of connection, so we will substitute the value of T1 equivalent to T2. So Mbg is equivalent to Fs. Okay, here. And then we have the Fs. Basically, friction is due to the multiplying coefficient of static friction by n. So there we can get the value of n. Okay, basically we have the n is a MAC. So mass of M, A and C, this mass. Okay, A and C multiplied by G. Okay, and then we have MAC is MA plus MC. So and then G is we can omit. Okay, slash out, and then the equation is finally something like this. Okay, in order to get the value of MC, so we will make the MC is a subject. Okay, and try to substitute the value, and finally we obtain the value of MC is equivalent to 5 kilogram. So this is the way. So maybe the certain condition of equilibrium can be given in different way. So maybe the question asking for the external force given maybe force pull by in this area, in this condition at a certain angle, so that required us to get the value of angle in order to avoid from the object or system to move. So many ways can be done or be asked by using this kind of equivalent in the pulley system. So next we will go for the friction on the ladder. So the ladder also play very important part in the application. So that we have the condition of floor and wall have a friction, whereby we have the this point at point B and at point A, whereby the wall and the floor have a friction, and other condition whereby the floor has friction but the wall is frictionless. Okay, what will happen to this condition? Two conditions: the floor and wall have friction, so that we can produce a free body diagram is something like this. Okay, so in this case of number 2, we don't have the friction from the FSB. So FSB is produced from the point of B. Fs indicates for the friction, static friction. Okay, so some of the textbook the differentiate by using FB is the normal force of the at point B, and FAY is normal force at point A. So they use N here and N here. Okay. So in this case, we have the ladder. So by using the ladder, we need to get the concentrated force, okay, at ladder, be at the center. Okay, if the given the distributed force, maybe we can get the value of concentrated force. Okay, so that okay can be easy to solve the problem. Okay, please let's see from the condition of the ladder length L and a certain mass, okay, M, rest against a wall. Its upper end is a distance of h, okay, b at h height. Okay, the center of gravity of the ladder is 1/3. Okay, center of gravity here is 1/3. Okay, from A. And then a firefighter, let's assume that the black box is a firefighter climbing halfway up. So halfway the center, in the middle of the ladder. So halfway we have the distance from this is A over 2. Assume that the wall but not the ground is friction. Okay, the wall is friction, the ground is friction. The wall is frictionless, the ground is friction. Okay, so that what is the force exerted on the ladder by the wall and by the ground. So you need to identify the reaction. Okay, reaction force, normal force here and also normal force here. Okay, the wall and the ground. So how we manage to solve this? I think we need to draw a free body diagram. Okay, so we need normal force is FB. Okay, FB here, and then we have FAY. Okay, or from this point A we have two forces acting. Okay, FAY and SA. Due to the ladder will slide to this right the left side, so the friction will be counter, okay, direction. So from this we have a normal force here, but no frictionless, so there is no force acting on upwards. So for the first thing we need to highlight is to get the uh, equilibrium condition of Fx equal to 0 and Fy equal to 0. In this case, we have Fx, we have only value of Fb and Fsa. So this both value is about the same magnitude, different direction. So for the Fy, we have three arrow of in blue color. So Fay positive, two value of blue color mg, and this mg we minus this value and equal to 0. We cannot if we use these two equilibrium, we cannot solve this problem because we have three unknown. Okay, the unknown from the unknown from the FSA, FAY, and MG. Okay, so we cannot solve this problem. So we need extra equation to solve this problem by using moment. Okay, by using moment as equation number 3, so we can put the moment at A. So once we put moment at A, we can have a three forces acting on point A. So we have mg, this mg, and then fb. So it's equivalent to 0. So once we put the moment, so we have fbh minus mg a over 3 and minus MGA over 2 equal to 0. Okay, so from here we can make it FB as a subject. Okay, we can get the value of FB, okay, by simplify the equation. Okay, and finally we have something like this. Okay, so please be remember that the value of FB and FSA is the same. And so once we have the value of FB from the moment we substitute in this equation, so the FSA is equivalent to FB. Okay, once the value we have, we substitute the value and finally we have the value FSA and FFB. Okay, okay, let's see from the problem number C. So related to the ladder, so we have given the ladder lean AB leans against a wall as shown. Assume that the coefficient of static friction mu s is 0 at B. So in this case, the wall is frictionless. So A at A is a friction. So the first thing which free body diagram, B determine the smallest value of mu s at A for which equilibrium is maintained. So what is the value of at A in terms of coefficient of static friction. So it will maintain the ladder at that position. So it will not sliding down. What is the minimum, the smallest value? So in this case, we produce a free body diagram here, and then we start to compute the value of mu s. So in this case, we have the net force Fx equal to 0. So in this case, we have Fs equal to Fb. If as equation number 1 and equation number 2, we have Fy is equal to 0, whereby Fy is, we have two value, Fay and equal to W. So and then we use the moment at point A. So the moment at point A, we have only two forces acted, which are W and Fb. So in this case, W is distance from point A is 2.5 divided by 2, which is 1.25. And in terms of FB, from point A, the distance is 6. So we have 6 FB equal to 125 W. So we have three equations, so we can manipulate this equation, whether divide or substitute. In this case, I use divide equation number 1 to equation number 2. So we have Fs divided by Ay equal to Fb divided by W. So and then by using and then we put as a equation number 4. By using equation number 3, we substitute the value of W into the equation number 4. And finally, we have something like this for the F has divided by FAW. Okay. So and then the substitution is something like this, and FB we cancel it out. And finally, we have Fs divided by Fay equal to 1 to 5 divided by C. So actually, the Fs divided by Fay is a tangent theta, basically, and is equal to mu s. Okay, and the value is 0.2083. So the minimum value of mu s is basically the value of 0.2083. Okay. Okay, another way maybe you can substitute by using the Fs here. Okay, the same thing process, but you from Fs here, maybe we can substitute by using the friction force. Okay, mu s Fay here. So from here we get the connection is something like this, and then you substitute, and finally you will produce mu s. Okay, there's two way can be used to solve this problem. Okay. Okay, problem 7, which is both A and B is a friction given value of determine the small value of mu s at A, which equilibrium is maintained. Maybe we can proceed in something like this. So you start to write to make a free body diagram. Okay, and we have basically FB as a normal force. Okay, FB as a normal force and FAY is a normal force. In order to get FAB, basically we will FSB, basically we multiply normal force here, FB by mu s, and also in order to get Fs, we multiply Fay to coefficient of static friction or mu s. Okay, so we will start to, okay, you can start by using Fx equal to 0, Fy equal to 0, and Ma equal to 0. So in this case, make it fast. We start Ma equal to 0. So we manage to get only three forces acting: W, Fb, and Fsb. So here we have this. Fb we have 6, Fsb we have 2.5, and W we have half of the 2.5 here. So once you you get the equation, and then we substitute the value of Fsb here, and it's make it something like this. And then Fb, so Fb in the term of W and mu s here we get, so we state as a equation number 1. Okay, and then we have the Fy equal to 0. So Fy we have the only three forces, which is Fay, W, and Fsb. Okay, once the equation is something like this, so Fsb we substitute by using this, and we get the value of something like this. Okay, so and then we make it as a equation number 2. So we have the normal force F at Fb, okay, which is the value is here. Normal force Fay, which is the value of is here. Okay, and then we substitute the value of equation number 1 to equation number 2, and finally we get the value of Fay is something like this. Okay, and then we make it a equation number 3. Okay, so by using Fx equal to 0, we know that Fs and Fb is equivalent. So we will substitute the value of Fs, okay, by using this formula. Okay, and then we have the term of Fay and Fb. Okay, from the previous slide we obtain the value of Fb here and Fay here. So we have equation number 1 and number 3, we will substitute in equation number 4. Finally we simplified, and we managed to get the value of mu s, which is two value. One is 0.2 and the second one is -5. So -5 we will omit So the value of the mu s is 0.2. And then maybe this is the exercise number 2 for you. Try to get the answer, okay, with a different question. Okay. And finally, we will look at the different application in problem 8. So we have the bracket, okay, which is a bracket slide on the cylinder. So we have this bracket applied with the external force of W here at the distance from the center of the cylinder, which is X, and then given from this bracket to higher and lower bracket, we have 150 mm, and the diameter given to 75 mm. So in this case, if the coefficient of friction between the pipe and bracket is 0.25, so asking for the determine the minimum distance X, okay, at which the load can be supported. Okay, so we load given, external load given here, what is the minimum distance? Okay, how far we can produce, can give the external load, how far from the center of the cylinder. Neglect the weight of the bracket. So the first thing we need to do is produce a free body diagram. Okay, this one is we have two friction produced here is from the upper and from the lower. Okay, collar here. Okay, this can at the maximum value of the friction, and then we have the produce a free body diagram of bracket contact at the this bracket contact with the cylinder, and then apply condition for static equilibrium to find minimum X. Okay, so let's see what happened. So first thing, we need to produce a free body diagram. We know that once we produce a external force here, okay, and here is a cross sectional area of the cylinder from here and from here. So the point contact, if we apply this force, will produce here and here. Okay, these 2 points from here and here. Okay, once we give the external force here, it will produce at point A and point B here. Okay, so at this point we can make a free body diagram. We have the normal force NA and FA here. Okay, because this bracket will start to move downward, so the FA is a friction force. Okay, and then we have FB and FNB. Okay, so for the FA, we can apply by using a formula of frictional force. So mu S and A. So given the mu S is 0.25, so we have 0.25 NA. And also for the FB, we have 0.25 NB. Okay, and then we apply condition for static equilibrium to find minimum X, so that we apply for Fx equal to 0. So for the Fx, we have Na and Nb is equilibrium. So we have Na equal to Nb as a equation number 1. And then we have Fy equal to 0. So Fy, we have three forces. We have Fa, Fb, and W. So Fa plus Fb minus W equal to 0. And we put as a equation number 2 after we substitute the value of Fa and Fb. Okay. So for the two equation, we substitute the value of Nb equal to Na to the equation number 2. So now the equation is, has the term of Na and W here. So we know, we make a simplified equation, and finally we have W is equal to 0.5 NA, or NA is equivalent to 2W, okay, whereby NA is equal to NB. Okay, to use a moment. Okay, we know that W at a distance from the center of the cylinder is X, okay, whereby we know that the diameter of cylinder is 75 mm. So from here to here supposed to be 75 mm divided by 2, which is 37.5 mm, and the rest of here is X minus 37.5. So we would like to know the distance of W, which is X. So in this condition we have the distance from here to here is X minus 77.5. Why we need to this value is because we want to apply moment at point B. So once we know the moment at point B, so we will know the distance of W at point B, which is X minus 37.5. So at moment at point B, we have three forces which is come from NA, FA, and W. So for the FA, we assume that moment is counterclockwise. Okay, counterclockwise. For the FA is negative 75 FA. So from point B, the FA is distant 75 here, and then we plus 150 NA. NA is distant from B is 150, and we minus this W, whereby the distance W is X minus 37.5, which is here. And then we make a substitution of FA, which is FA is value here, and then we substitute the value, and we have the term of NA and W. So and then we simplify, we have NA, and W. And finally, we substitute the value of NA, which is the value is 2W, and also NB is equal to 2W. So we substitute this value, and finally we have the equation is something like this. So and then in order to get the value of X here, so we divide by W. As you can see, all term here is in containing is W here, W and W. So by simplify the equation, we have still 300 W over W. So finally, in for the distance W external load given from the center of the cylinder is 300 mm or 0.3 m. So as you can see here, W is already cancelled. So W is no more in the involved in this condition. So note that W is doesn't matter W is given, is does make any difference. Okay, so does it make sense? Okay, so maybe you can figure out. Okay, so I have several equation, so maybe you can try to solve the problem and I give the solution, the answers. So please try to get the answer here. So this, okay, and certain maybe if you have you browse the internet and get the different equation, different question, so try to get. Okay, so this one, Okay, try to solve this problem. Okay, so thank you very much. I hope you all can understand. Okay, this is the second last of our chapter. Later, uh, next week, I will upload another the final chapter, part B of this friction, which is the chapter 7. So after this, we will finish our lecture. So thank you very much. Bye bye.